or it's sometimes called Faraday's law. So this chapter will cover 2 lectures, so today and Monday. So Monday will be an in-person lecture. By the end of this lecture, so you should be able to determine the magnetic flux through a surface, use Faraday's law to determine the magnitude of an induced EMF, so induced voltage in a closed loop, use Lenz's law to determine the direction of the induced EMF and an induced current, use Faraday's law with Lenz's law to determine the induced EMF in a coil and in a solenoid, and finally determine the magnitude of an induced EMF in a wire moving at a constant speed through a magnetic field. So let's start with the first part of this lecture. So first, Faraday's law. So before we jump into explaining what is Faraday's law, I just want to remind you what are the key equations we've seen last time. So basically last time we were linking the existence of magnetic field through flowing currents. So flowing currents are due to electric field. So we have seen the force between 2 parallel currents. So the force per unit length, FB over L, is equal to μ0 I1 I2 divided by 2 pi A. I1 first current, I2 second current, A, the distance between the 2 parallel currents. If I1 and I2 are flowing in the same direction, then the force is attractive. Here they're flowing in opposite directions, then the force is repulsive. We've seen the magnetic field at the center of a single turn current loop, μ0 I over 2A, where A is the radius of the loop. And if you have n turns, you have to multiply this equation by capital N. We've seen the magnetic field inside a solenoid, which is B equal μ0 lowercase n times I, where n is just capital N, so the total number of turns divided by L. The length of the solenoid, so a lowercase n is the number of turns per unit length. And finally, we've seen the magnetic field inside a toroidal coil, which was μ0 capital N I divided by 2 pi R, where capital N is the total number of turns in the toroidal coil, and R is the radius at which you want to calculate the magnetic field inside the toroid. So what we've been doing basically is we were linking electric field and magnetic field. So we've seen that there are many similar features between electric field and magnetic field, and most scientists believe the two fields must be somehow related. So in 1820, Ørsted discovered that the magnetic field due to a steady current where you could create magnetic field with steady current, and it showed the first clue of such a connection. So we know like electric field drives the current, the electrical current, and that those current induce a magnetic field. So what was left to do is to find the reverse connection. So how magnetic field are linked to electric field. So that was the work of 2 physicists. So first Michael Faraday in England, and shortly after Joseph Henry in the USA, that found that a changing magnetic field induces an electric current in a nearby coil of wire. So therefore, this was the first glimpse of the long thought connection between magnetic field and electric field. So I will show you 2 demonstrations. So the first demonstration is very strongly linked to the illustration you have here. So when you have a non-moving magnetic field close to a loop of wire, then there is no induced current in this loop. But if it happens that you move the bar magnet towards the loop, then you will measure a current inside this loop. And if you move the current away from the loop, then you will find a current in the reverse direction inside the loop. You can do the same with solenoid, and that's what we will do. We'll see in the 2 demonstrations. So here's the first demonstration.
A demonstration, which is very much like what you see here. I have here a loop. That is the square that you see there, except that it's not one loop, but it is many of them. Hundreds, doesn't matter. And what we're going to show you is an ammeter that is connected. So there's somewhere in this circuit an ammeter. I have a bar magnet, and I'm going to approach this conducting loop with a bar magnet. And you're going to see a current running in one direction, and when I pull it out, it will be running in the opposite direction. And when I hold my hand still, so that the magnetic field is not changing, no current. You're going to see the current meter there. And here is my bar magnet. I come close to this conducting loop. Notice, you see a current. I pull back, current is in the other direction. Now I will go faster, so that the change of the magnetic field per unit time is stronger. More current. I go out fast, more current. So you see, it's the change of the magnetic field that matters. If I come in very slowly, which I do now, very slowly, you almost see nothing. And right now, the entire magnetic field is inside this loop. The strongest I can have it. Nothing happens because there is no change in the magnetic field. It's only when I do this that you see the current.
All right, so that was our first demonstration with magnet, and now let's see what happened when we use coil.
There, a very sensitive amp meter. And you're going to see here this loop, the big wire, and I'm going to just put it over this solenoid. Let me first make sure that my amp meter, which is extremely sensitive, I can zero it. It's sign sensitive. If the current goes in one direction, you will see the needle go in one direction. If the current goes in the other direction, you will see the change. And so now I put this loop around here. Crazy shape, this loop. So it's around this solenoid once. So the magnetic field is inside the solenoid. And so think of a surface which is attached to this crazy loop. And now I'm going to turn the current on, and only while the current is changing will there be a changing magnetic flux. Only during that portion will you see a current flow. 3, 2, 1, 0. I will break the current, 3, 2, 1, 0. Went the other direction.
All right, so what is the main information you got from those two videos?
Magnetic field movement is required to create current?
Yeah, that's very good. So basically, a change of magnetic field is required to create electric current. And so the exact terminology is exchange of the flux of magnetic field through the loop is necessary to create current. So if you have a static magnetic field in a loop, there won't be current. But if you have a moving magnetic field, which induces a changing magnetic flux, then you will have current. So first of all, we will need to define what is a magnetic flux. So you probably have seen what is an electric flux with Professor McWilliams. This was linked to Gauss's law. So the idea is almost the same. So here you take an area, A, so that's the orange part you see here, and you have a magnetic field, which are the blue line here. So the magnetic flux is a measure of how many magnetic field line passes through the given area A. So the flux is maximum when the magnetic field lines are perpendicular to the surface, and the flux is 0 when the magnetic field lines are parallel to the surface. So you can make a comparison with like fluid flow. So for example, air. So if there is wind and I take my notebook here and I'm facing the wind, so the surface area of my notebook is maximum with respect to the wind flow, then you will feel a very strong force pushing on the notebook. Now, if you take the side of the notebook, so the surface area is almost 0, then the surface of the notebook is actually perpendicular to the flow, and the force is almost 0, and that's because the flow through the notebook now is 0. So this is an analogy between flux and classic fluid flow. So actually flux and flow is the same word in Latin. So that's a way to remember how to have a feeling about the flux. You can see this as a fluid trying to go through the surface. So if the area of the surface is facing the flow, facing the current, then the flux is maximum. If it's at an angle of 90 degrees, then there is no flow going through your surface. So let's try to quantify this a little bit more. So in this area, you can always define a unit vector n hat, which is normal to the surface. So that is black vector here, n hat. And this n hat vector can make an angle with the magnetic field. So this angle theta, when the magnetic field is parallel to n hat, so or perpendicular to the surface, then the angle is 0 degrees and the cosine of theta is 1, and we have a maximum flux. Second case, second extreme case, then the magnetic field lines are perpendicular to n hat. Okay, perpendicular to n hat means the flow is actually parallel to the surface. Then the angle is 90 degrees, the cosine of 90 degrees is 0, and then we have a minimum of the flux. So when we have an arbitrary angle theta, then the cosine is lies between 0 and 1, and we have intermediate value of the flux. So this n hat vector is very, very important to actually calculate the flux. So in mathematics, the area is represented as a vector quantity. So a vector area, capital A vector, is A, so a number in square meter times n hat. Okay, so n hat is a unit vector perpendicular to the surface. Then in terms of n hat unit area vector, normal to the surface, and based on the previous slide, we can conclude that in general, the flux will be proportional to B vector dot product n hat. Okay, and that's what we have here. If they are parallel, then in the dot product, the cosine is cosine of 0, we have 1. If they're perpendicular, then the dot product is equal to 0 because the cosine of theta is equal to 0. So to define this more appropriately, we can always consider a small differential area element represented by delta, capital delta A vector equal n hat capital delta A. So it is a small element that you can cut on the surface here. That would be delta A. And if we add the n hat vector like that, we can also define the delta A hat. So the magnetic flux through this differential area element is then delta phi, capital Phi, equal B vector, dot product, sorry, capital delta A vector, which you can rewrite as B vector dot product n hat delta A. Okay, so note that we have a dot product, so the flux is a scalar quantity, it's a number. Okay, for this calculation, we are making the assumption that in this small area here, B can be treated as a constant. Okay, so in the small area here, B is a constant, which is not necessarily the case through the entire surface. Yes, Benjamin?
How would we determine the difference between like the symbol for magnetic flux or electrical flux, or do they use the same symbol, or is there
so
a
here
small...
I will come to that. So here we're using phi is a general symbol for flux. When you can have a confusion, and it can happen in some problems, then you will write phi with a B index next to it, so it's phi magnetic. Okay, so I will do that in the next slide actually. So that's what I do, not here, so but yes, I mean, in the next slide when there can be a confusion, I will write phi B instead of just phi. But here there is no confusion because we're just dealing with magnetic field. All right, so the magnetic flux through the differential area element delta phi is by B vector dot product n hat delta A, or independently B vector dot product delta A vector, and its unit it's Weber, and Weber is defined as Tesla times square meter. So B Tesla, and this is an area, so square meter, so the result is Tesla square meter. So in general, if you start from the magnetic flux through a differential surface area element, so a very tiny element here, delta A, you will obtain just a differential flux, okay? It's not the total magnetic flux through the area. If you want the total magnetic flux, you have to cut your area in many differential elements delta A, and then you have to make the summation over all the surface of those elements of flux. So this is very similar to what you've been seeing with electric flux. Okay, and for magnetic flux through a surface, so as a convention, we write phi, and here I put the index B to insist that is the magnetic flux. It's the integral over the surface over B dot product dA. Okay, so because when you make the summation here, the differential element, differential area A here has to go towards 0. So this like finite sum here with capital sigma become an integral over the entire surface of B dot dA. And we will see later that the Faraday's law of induction states that an EMF epsilon, so a voltage epsilon, is induced in a loop when the magnetic flux through this loop changes with time. So mathematically, epsilon is equal to minus the derivative with respect to time of the magnetic flux. Okay, so d over dt, this is derivative with respect to time. Okay, so in mass, normally you define function as f of x, and the derivative is f prime of x. Okay, in the physical world, a function is not a function of only one variable. So typically a function will be f of x, y, z, because space is in 3D, and it can also depend of time. So if you write f prime, you do not know with respect to which variable you differentiate. So a derivative with respect to x, you can write as d over dx of f of x, y, z, t. The derivative with respect to time is d over dt over x, y, z, t. All right, so if you know derivative, it's just a different notation, and just keep in mind that the d something, so x in this case or t in this case, just tells you what is the variable, and everything else can be kept as constant. Is that okay for everyone? All right. So now that we have defined the magnetic flux, so mathematically, so we go from delta A to dA, so it's a limit. So when delta A goes to 0, the sum becomes a surface integral, and so we define the magnetic flux through a loop of area A by phi or phi B for magnetic flux as the integral over the surface of B dot product dA, where dA equal n at dA, and the result is in Weber. So if you have a loop like that, the area is defined by the area which is enclosed by the loop, and you can attach, for example, a normal vector n at here to this surface, which will be perpendicular to the surface. So when we were defining the differential flux, so the delta phi here, we were assuming that B can be treated as a constant, but it's treated as a constant only on the small area delta A. When you deal with the entire flux, B is not necessarily a constant, okay? It can change over the surface area, okay? So that's why B is inside the integral and not outside of the integral, because B is not necessarily a constant through the entire surface. Okay, so this is a general case. In most problems you have to solve, B will be considered as constant over the surface area A. But in general, and if you deal with real-world application, you will have to take into account that B is not necessarily a constant. All right, so how to use this now? So we can calculate the magnetic field. So here, example where we will consider the magnetic field as a constant through the loop area A. So this is our loop. because here we're just discussing concept. And in that case, the magnitude of the magnetic field B can come out of the integral. You still have to do the dot product. Therefore, you have the cosine theta appearing. And the result of this integral will just be magnitude of the magnetic field times surface area of your loop times the cosine of the angle between the loop and the magnetic field. So for example, here, the n hat vector will be parallel to this dotted line here. So that will be our n hat vector. So therefore, for the Lenz law, so Lenz law was given here, derivative with respect to time of the magnetic field. What does it mean? If your magnetic field changes with time, or the area changing with time, or the angle changes with time, then you will induce an electromotive force or a voltage on the loop. Okay, so the magnetic field can change with time if it's induced by a solenoid, for example, in which you have a changing current. So if you remember, for a solenoid, you have the magnetic field, which is given by mu0 and I. So if I is a function of time, then B is also a function of time. So therefore, you can have a derivative with respect to time. If the area of the loop changing with time, so for example, you have a loop that can increase in size or decrease in size with time. Same thing, A became a function of time, so its derivative with respect to time exists, and it will induce an EMF. The cosine of theta can change, like this loop, for example, can rotate in time. Therefore, this angle will change. And if you have theta, which is a function of time, then the cosine of theta is also a function of time, and the derivative with respect to time will exist. So before we jump into examples on how to use that, can you think of very, very important application that derives directly from Faraday's law of induction?
AC generators?
AC generator, yes. That's a very, very good application. Other thing? So there's guitar pickups that are an application as well, and to some extent, you also have electric motors that if you've been using electric motors, you know, like when the motor is actually on, you have a back voltage on the motors. They have to take into account when you use that in an electric circuit. But the main application is actually AC generators. So like the alternator of your car or the dynamo of your bike, or I mean a power plant, like a coal power plant or a nuclear power plant or a hydro power plant. What you do is you have like magnets turning in middle of coil, which is the same as a coil turning around magnets. So you have a changing magnetic flux through coils, and that's how you convert this mechanical power to electric power. Okay, so Faraday's law of induction explains why we are able to generate electricity. Okay, that's how we can convert like mechanical force, so something rotating, so like steam, like in case of a coal power plant. So you burn coal to make steam, and the steam will be used to rotate coil and magnet. Same for hydro, where it's just a gravity force that will make your system like of magnet and coil turning. And for a nuclear power plant, you're also producing steam and so on. So basically, Faraday's law of induction is very, very important in everyday life. Like, I mean, because we are able through changing magnetic flux to induce electric field and therefore electric current, that we can convert mechanical power into electrical power. Yes, Zainab?
I was just wondering, why is there a negative sign in the EMF equation?
I will come to that. I will explain it very quickly. So this is actually just after the example, I will explain why we have this negative sign. And that will be Lenz's law. Lenz's law will explain the negative sign. All right, so before we actually jump into the explanation of this negative sign, let's try to use this knowledge we already have to calculate some EMF. So here's a first example. And here I forgot to write down information, but I will add them on the fly. So here you have a square coil, which has side which are L equal to 0.515 meter long and is tightly wound with N equal 500 turns of wire. The resistance of the coil is R equals 6.25 ohm. The coil is placed in a uniform, spatially uniform magnetic field that is directed perpendicular to the face of the coil. Okay, and we know like this magnetic field will decrease from 120 Tesla to 0.5 Tesla in 12 seconds. So then we want to calculate the magnitude of the induced current, of the induced EMF, so which is the same as voltage. And we want to calculate the current in the coil. So let me remind you the given. So we have a square coil. Side L equal 0.150 meter. We have N equal 500 turns. And it has a resistance of 6.25 ohm. It's embedded in a constant, in a uniform, so uniform magnetic field perpendicular to the surface. And at B at t equals 0 seconds is equal to 1.20 Tesla, and B at t equal 12 seconds is equal to 0.50 Tesla. And the first question we want to answer is induced EMF. So how would you do that? Any ideas? No? All right, so basically we have to use what we have learned here. So the induced EMF is linked to Faraday's law. So this is the derivative with respect to time of the magnetic flux. Okay, so Faraday's law, epsilon is equal to, and we'll just deal with absolute value for now, derivative of the magnetic flux with respect to time. Okay, so what do we need to do? So this is Faraday's law. So we need to find first, so what is the magnetic flux? So phi b is the integral over the surface of the coil of B dot product dA. And we know we have n turns, so we have to multiply by n. Okay, each turn of the coil will contribute to the EMF. It's the same thing as we've seen for induced magnetic field in solenoid, where you have to take into account every turn of the solenoid to calculate the magnetic field. So it's the same for the flux. You have n loop, so you have to multiply by capital N here to get the total magnetic flux through the coil. So let's try to calculate this. So if I look from the side. So side view, I can see like my coil. It's probably something like that. So the surface I can define here. So my n hat will be like that. Here I have a length L, and if I do a top view, I will have something like that. So with my n hat like that, and the B is going down. Up. So the B in the side view will be something like that. And in the top view, the B will be across. So what is the value in that case of my magnetic flux? Any ideas? So I can rewrite this as, so surface as B scalar n hat dA. How are B and N parallel or perpendicular?
Parallel,
Yes, so the dot product, what does it give me?
1.
Almost. I mean, it's, you have to take into account that B is not a unit vector. So it will give you B basically.
Okay.
So if we're just interested in the absolute value, so we just do that. So we only get positive quantity. So we get N, B scalar N hat is just B. And then we just have to calculate the integral of dA. This is a square. So what is the value of this integral? What is the surface of a square?
Length squared.
Yep. So our magnetic flux here will be phi B equal N B L square. So now that we have the magnetic flux, so we can now calculate the EMF epsilon. So this is directly Faraday's law. So we have epsilon equal to, in absolute value, the absolute value of d phi b over dt equal minus the absolute value of minus the derivative respect to time of n b L square. Does n depend on time?
No.
Does L square depend on time?
No.
So this I can pull out of the integral. So I have epsilon equal n L square, and I have minus d over dt of b. And in the text, we tell you that b depends on time. Okay, at t equals 0 seconds, it's 1.20 Tesla, and at 12 seconds, it's 0.5 Tesla. How can I estimate the value of the derivative with respect to time?
Your change in B over time, like
Exactly, delta b over delta t. So I can approximate this as n L square of delta b over delta t. And I have everything I need. So delta b is just 1.2 Tesla minus 0.5 Tesla. So this is equal to 0.70 Tesla, and delta t is just 12 seconds. So I have my epsilon, which will be equal to 500 times 0.15 meter square times 0.70 Tesla divided by 12 seconds. And then we get epsilon, which will be equal to 0.656 volt. So the second part of the exercise was B, calculate the current in the coil. And one given that we have to use is R equal 6.25 ohm. So you probably have seen that during term 1. So what is the relationship between voltage, resistance, and current in a circuit?
V equals IR.
Yep. So V, which in our case, the same as epsilon, is equal to I times R. So what is I in our case then? So that is Ohm's law, by the way.
Epsilon over R.
Epsilon over R. So I have everything I need. So I have I equals 0.656 volt divided by 6.25 ohms, and I have I, which will be equal to 0.105 amps, which is the same as 105 milliamps. All right, so now let's complicate a little bit the exercise. So we take the exact same coil as was described here. The main difference now is the surface of the coil makes an angle theta with respect to the magnetic field. So in case A, theta will be equal to 30 degrees, and in case B, theta will be equal to 45 degrees. So how do I need to modify the result I just got? So for theta equal 0 degrees, I got epsilon equal to 0.656 volt and I equal to 105 milliamps. So what do I need to do to get the result for theta equals 30 degrees and theta equals 45 degrees? Where is the main difference with the calculation we did?
Dot product.
Yes, exactly. So the main thing is when we calculate the flux. Okay, so the flux was N, capital N, because we have N turn, and then over the surface of the coil of B dot product dA. Okay, so the dot product at 0 degrees, we just obtain BA, basically BL square. When now I have an angle, what do I need to add to the answer?
Cos theta.
Exactly, cos theta. Okay, and this cos theta comes from the dot product. Okay, at 0 degrees, cos theta is equal to 1. You just obtain BL square, NBL square, because you have N turn. Now you have in the dot product between N hat and theta, you have to take into account the angle, and the dot product makes a cosine theta appear. So the only difference in your answer is this cosine theta. Everything else is the same. So from there, since I know like everything else is the same, what is epsilon at 30 degrees?
Uh, 0.568 volts.
Yes, and how did you obtain that?
I multiplied the original epsilon by cos 30.
Exactly. So this is epsilon at 0 degrees times cosine theta. Theta equal 0 degrees, so cosine theta equal square root of 3/2. And you can put this in your calculator, and epsilon at 30 degrees will be equal to 0.568 volt. And what will be the current then?
$90.9 milliamps.
Exactly, so 90.9 milliamps, and you can calculate it in two ways. You can either use Ohm's law, so you have I equal epsilon 30 degrees over R, and you will obtain the exact same thing, or you can use I of 30 degrees. I of 30 degrees is just I of 0 degrees times cosine 30 degrees. B theta equal 45 degrees. It's the exact same technique. Cosine theta then is square root 2/2. So you will obtain epsilon of 45 degrees equal epsilon of 0 degrees times cosine 45 degrees. And this will be equal to 0.464 volts. And the current at 45 degrees will be equal to either epsilon of 45 degrees divided by R, or I of 0 degrees times cosine 45 degrees, and you will obtain 74.2 milliamps. Does that make sense for everyone? Yes? So no question? All right, so now let's move to the explanation of this minus sign here. So you had Faraday's law, you had this minus sign here. So where does it come from? So that's what is called Lenz's law. So Lenz's law explains this minus sign. So this is this negative sign in Faraday's law, and it tells us about the direction of the current driven by the induced voltage, by the induced EMF. So if in a wire, in a conductor, you have an electric field, so a difference of voltage between one end and the other, then you drive a current, okay? And this minus sign tells us in what direction we have the electric field, so therefore in what direction we drive the current. So Lenz's law states that the induced current tries to keep the original magnetic flux through the loop from changing. Okay, so you can rephrase this as the induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. So here I've included another demo from Penn State University that you can watch at home if you have downloaded the lecture notes. And I will just explain this with some illustration taken from the book. So here you have this current, this loop of wire, so it's conductor loop. And you have a magnet, so north pole here, south pole here. And this magnet can move towards the loop or move further from the loop. So case A, the magnet will move towards the stationary conducting loop. And what you will experimentally see, and that's what the demo I show you at the beginning of the lecture, is there will be a current infused in the loop. And here in green, that's the magnetic field line due to the bar magnet. So Lenz's law states that the induced current tries to keep the original flux through the loop from changing. Okay, so in case A here, you have a magnet going towards the loop. So the magnetic field is getting stronger and stronger when you get closer to the loop. Therefore, the flux here, the flux of magnetic field through the loop is changing, is increasing. Okay, so Lenz's law states the current in the loop will fight this. So to fight this, it has to generate a magnetic field in the opposite direction. So to generate a magnetic field in the opposite direction, the current here has to flow counterclockwise, okay? So it's given by the right-hand rule. So you know, like the flux is increasing. The magnetic field here is directed toward the right. So the current phi is changed, so it has to generate a magnetic field toward the left. You use the right hand and you find immediately that the current has to flow in the counterclockwise direction, okay? The induced current in the loop produces its own magnetic field. That's what we've been seeing last time. If you have a current in a loop of wires, then you create a magnetic field. And this magnetic field is directed to counteract the increasing external flux, okay? Lenz's law says you want to fight the change. Case C, okay, so now the magnet is going away from the loop, okay? So the magnetic field strength at the level of the loop is getting weaker and weaker. That means the flux through the loop is getting weaker, okay? So if it's getting weaker, the flux is decreasing, so the current induced in the loop will try to fight this change. So the current has to create a magnetic field that generates a magnetic field which is in the same direction of the applied magnetic field. So the flux, the change of flux is not as important. Okay, so you are fighting the change. Again, you use the right-hand rule and you will find that in this case, so the electric current generated in the loop has to be in the clockwise direction. So the induced current in the loop produces a magnetic field directed to the right and so counteract the decreasing external flux. Does that make sense for everyone? So the minus sign here in the Faraday's law is due to keep the original magnetic flux through the loop from changing, okay? Or induce current in the loop in the direction that create a magnetic field that opposes the change in magnetic flux. So this opposition is given in the minus sign. So makes sense for everyone the way you guess the direction of the current in the loop? Okay, let's try to apply this then. So now you put your eyes here, and that's where you observe the direction of the current, and you have this bar magnet. So south pole directed towards the loop, and it moving from the left to the right. There is three configurations to take into account: A, B, and C. So we'll start with A. In what direction is the current in the loop in this case?
Clockwise.
And why?
Because the magnetic field by the magnet is going towards us, and so the opposing would be going. The current would make the magnetic field opposing would have to go in to the paper, and which means that with the right-hand rule, it would have to be going clockwise.
Exactly. So I will just draw what you say. So magnetic field line are going towards us like that. It's a south pole. So the flux here is increasing because the magnet is getting closer. So the magnetic field that will be generated to fight the change, I will draw it in blue, will be in this direction. So the B induced. Sorry. And therefore, if you use the right-hand rule, you have the current, which is like that, counterclockwise. Oh, is it? No, clockwise. Sorry. Yeah, clockwise. All right, case B. So case B, what is the induced current? So case B, magnet in the middle of the loop. So if you have a top view that I will show here. So you have your loop like that, and you have your magnet right in the middle. With the source pole here. And the north pole here. So what is the induced current now here?
Counterclockwise.
And why?
Because the electric field lines go from north to south. So in the middle, they'll be pointing into the page, which means using the right-hand rule, we'd have to get counterclockwise current for an opposing.
So you're almost there, but there's one thing you forget. Okay. Here the magnet is right in the middle of the loop. Okay, so can the flux still increase there? Or decrease?
Would it be just 0?
Yes, because you're at maximum flux. So when you have your magnet moving here, if you just plot the absolute value of the flux as a function of time, you will have something like that. Okay, this is time. So case A, we're here. Case B, we're here at the top. Okay, so you have a maximum of the flux. So what does it mean for time derivative when you have a maximum?
Rate of change is 0.
Yes, so it's 0. So basically here in B, you have no current, no induced B. Okay, and now case C, what would be the direction of the current? So the magnetic field line now are like that. So what should be, is the flux in case C increasing or decreasing? Sorry, north pole. Line are like that. Is the flux increasing or decreasing in case C?
Decreasing.
It's decreasing. So the current generated by the loop, is it directed to the right or to the left?
Counterclockwise.
Yes, so the magnetic field will have to be generated like that, be induced. Okay, so that's case C. And you use the right-hand rule, so that would be, so C counterclockwise. Does that make sense for everyone? Yes? All right, so let's use this in another example. So now we will consider this situation there. Okay, so we have a solenoid, a long solenoid that has 1,000 turns per meter. And the current in this solenoid is a function of time. So it's 10 amps times 1 minus exponential of minus 2.50 multiplied by t being the time. Inside this solenoid, we have a small circular 150 turn loop of diameter 5 centimeters, which is placed inside the solenoid with the axis of the loop parallel to that of the solenoid. Okay, so here in this schematic, the small loop has basically the same axis as the solenoid. So we want to calculate the induced EMF in the small coil due to this changing current. And after that, we'll try to guess the direction of the current inside this small circular loop with 150 turn. All right, so for solving this, we need to go by step. So the first step, like any exercise, is to state the given. Okay, so the given are long solenoid, okay, n equal 1,000 turn per meter, and we have a current I of t, which is equal to 10 amps times 1 minus exponential minus 2.50 times the time. Inside this solenoid, we have small circular loop, diameter d equal 5 centimeters, capital N equal 150 turn, and we have axis of the loop parallel to axis of the solenoid. And the question is calculate the EMF in the loop, in the small loop. Any idea of what are the steps to actually get to the answer? What would you do? No one? Well, the first things to do is we have a solenoid here with a current inside. So we know from last lecture that this will induce a magnetic field inside the solenoid. So the first step is magnetic field in the solenoid. Okay, so I will remake a schematic of the solenoid. So here we have currents going in, here going out. And I will call the axis of the solenoid. I will call this the x-axis. So what is the magnetic field inside my solenoid?
Mu naught n current.
Yes. And what is the direction of this magnetic field?
I don't know.
So if you use your right hand rule, okay, you curl your hand the same direction as the current.
Negative I hat.
Exactly. Okay, and this you get with right hand rule. So we have the magnetic field created in this loop. Okay, and this magnetic field B is actually a function of time because mu 0 n, and we have I of t. Okay, I of t, it's a given. Okay, we know that the current is a function of time. Therefore, the magnetic field is also a function of time. So now if we want to be able to get to the EMF, we need to find the magnetic flux through the small loop, the small coil. circular coil. So the magnetic flux here, phi b, is equal to capital N, because we have N turns of wire in the coil, of B dot product dA. Okay, so here in the schematic, my small loop will be something like that. So my n hat vector, I can put it like that. So what will be the result of this BDA then? Okay, n hat vector is perpendicular to the surface, therefore parallel to the axis of the solenoid. So what is the result of this integral? So this is surface defined by circular loop. What is the result of this integral? Is the magnetic field parallel to the surface or perpendicular to the surface of the loop?
It's perpendicular to the surface.
So is it so B is perpendicular to n hat or parallel to n hat?
Parallel.
So therefore, what is the result of this?
It's 1, or B.
Yes, it's B times dA. Okay, the integral, no vector, surface defined by loop. Okay, and I will just put an absolute value here because actually right now we don't care about the sign. What is the surface of a circle?
Pi r squared.
Yep, and so here we have n b pi r squared, and r equal d over 2. So we have n b pi d over 2 squared, because in the given, we know the diameter of the loop. Okay, so let's just use the diameter as our variable. So now I have the magnetic flux. So I can get my EMF, so induced voltage, epsilon. So epsilon in absolute value is the absolute value of minus d phi b over dt. And I have my magnetic flux here. What is the only thing that depends on time in my magnetic flux?
The magnetic field.
Yes, that's what we calculated before here. Okay, magnetic field is a function of time. So we have epsilon equal basically n pi d over 2 square d over dt minus d over dt of phi of b of t. I can rewrite that because I know the expression of b of t. I have obtained it here. So I have n pi d over 2 square d over dt of mu 0 n I of t. Okay, what is the only thing that depend of time there?
Current.
Yes, so I can get mu 0 and n out. So I have epsilon equal to n pi d over 2 square mu 0 n d over dt of I, so absolute value I of t. So I know I of t equal 10 amps times 1 minus exponential of minus 2.5 times t. So what is the derivative with respect to time?
(2.5 e to the power of negative 2.5 t).
Almost. You still have to multiply by 10 amps.
Oh, okay, right. Yeah, sorry.
So 10 amps times 2.5 exponential minus 2.5 t. Okay, so now I'm almost there. So I can reinject this in the answer. So I have, and I will replace everything that I know. So n equal 150 turns times pi times, so 5 10 to the minus 2 meter divided by 2 square times 4 pi times 10 to the minus 7 Tesla meter divided by amps, that is mu 0, times 1000 turns per meter times 10 amps times 2.51 over seconds. Why do I know this t.50 here has to be the unit of 1 over second is because here in the exponential, this 2.50 here come from inside the exponential. You cannot have unit inside the exponential. So the unit of time is second. Therefore, the unit of this constant here has to be inverse second. Times exponential of minus 2.50 t. I can calculate all of this and I will obtain 9.25 times 10 to the minus 3 exponential minus 2.50 times time volt. Does this calculation make sense for everyone? Are the steps clear for everyone? Okay, so I repeat, when you have such a problem, you have the parameter of the solenoid, the current going through it. So the 3 steps: first, calculate the magnetic field in the solenoid, then calculate the magnetic flux through the second coil, and finally calculate the derivative of the magnetic flux to find the induced voltage in the current in the loop of conductor. Okay, so this is a classic problem. Okay, this type of problem is a very high chance that you'll get it either in assignment or in the module test. Okay, this is a classic problem. So now we have the answer, but we're gonna try to use Lenz's law to find actually the direction of the current in the loop. So we have calculated that the generated magnetic field was like this, B, I will call S like solenoid, and it was in the minus I hat direction. Is this current an increasing current or a decreasing current? So is the current at time equals 0 bigger or smaller than the current after a very long time? Let's try to calculate it. I of t equals 0 is equal to 10 amps, 1 minus exponential of 0. What is exponential of 0?
1.
Yeah, so 1 minus 1 is 0. So what is the current at time t equals 0?
0.
So we have 0 amps of current at time t equals 0. I at t goes towards infinity. So we have 10 amps 1 times 1 minus exponential of minus infinity. What is exponential of minus infinity?
I don't know.
0.
Yes, 0. So what is the current at time when time goes to infinity?
10 amps.
10 amps, exactly. So is it an increasing current or a decreasing current?
Increasing.
All right, so the magnetic field then induced in the solenoid is increasing or decreasing?
Increasing.
So you have an increasing magnetic field. So the flux through the small coil is increasing or decreasing?
Increasing.
So therefore, in what direction should be the induced field?
Counterclockwise.
So the field first, not the current, the field, the magnetic field.
Sorry. Positive I hat.
Yeah, so B induced is like that. So now how must be the current?
Counterclockwise.
Yeah, so you use the right-hand rule and the current must be counterclockwise. Exactly. Does that make sense for everyone? Yes? All right, so we're gonna finish with one application. So one application is actually the guitar pickup. Okay, so some of you probably play the electric guitar and you've probably seen those pickups. So those pickups here, you have like these bar magnets and you have a pickup coil and you have the magnetized portion of the string. So when you play the guitar, this string is vibrating and therefore the magnetic flux through the pickup coil will change. And if you have a changing magnetic field through a coil, then you induce a current, and this current you can send it to an amplifier and you can reproduce the vibration of the string. And vibration of a string for a guitar is the sound. Okay, so that's how you go from the vibration of the string to a sound on your amplifier by converting first the mechanical motion into electricity, and then this electricity back to mechanical motion, so the sound in your speaker. Okay, so this is another application of Faraday's law. Okay, any question?
Just a clarification. In the induced direction is always opposite to the actual force of the magnetic field.
It's opposite to the change. Okay, so it doesn't mean that it's the direction of the magnetic field. So if you go back to this case, for example, here, the magnetic field is getting stronger and stronger. Okay, but actually when you get inside the loop, that's the field, that's the flux that is getting stronger and stronger. You have more and more magnetic field lines passing through the loop. Okay, and because here it's a source pole, okay, the induced magnetic field has to be in like towards the right. Okay, it will be a north pole, the magnetic field will be in the other direction. Okay, that's this case here, magnetic field in the other direction. So that's not the strength per se that counts, that's the direction of the change. Okay, you can start from very close to the loop with a very strong magnetic field. Because you are decreasing the flux, when you go away, you will generate a field which is in the direction of the field of the magnet. That will be, for example, case C here is related to case D. Okay, so what matters is not the strength of the field, but the direction of change of the flux. Okay, if you are decreasing the flux, you have a magnetic field in a direction that wants to keep the flux constant, and if you are increasing the flux, you are generating a magnetic field that want to decrease this flux. Okay.
Thank you.
Actually, there is a funny application with the flux. So you might have seen that on TV or on a science show. When you have a superconductor and you put a magnet on top of a superconductor, what happens? No one have seen this kind of trick?
They float?
Yes, they float. And this is actually due to this Faraday's law. So we'll discuss this in detail later, but I mean, any piece of conductor, I mean, you can cut it into small loops. Okay, so if you have a piece of superconductor, if you bring a magnet close to it, well, you are changing the flux through this superconductor. And because this is a superconductor, when the current is flowing through it, there is no losses. Okay, there is no Joule effect. There's no heat, so you don't lose energy. So the flux of current will create a magnetic field, which exactly opposes the change of magnetic flux. So this will exert a force on the magnet you try to bring close to the superconductor, and this will make the magnet float. Okay, so this is due to this effect. Okay, we'll discuss this in detail later. This is called eddy currents. So eddy currents is just Faraday's law applied to big piece of metal, but that is the principle. Okay, so you generate an EMF inside your superconductor. This superconductor generates a magnetic field. This magnetic field creates a force on the magnet that opposes the weight of the magnet. Therefore, your magnet is floating over your piece of superconductor. All right, so I'm going to stop here for today. So I stop at the same place as this morning with the first group. So next time we talk about motional EMF. So next Monday, this will be in-person lecture. So there will be real demos. It won't be YouTube video anymore. I will stay connected here till like 3:30. So if you have questions on the lecture or on the coming model test 1, please go ahead, ask them now. I'd be happy to answer them.
For the exam, do we have to be logged into Zoom?
So no, we have created a Zoom session. It's just in case you have question during the test. So if you have a question during the test because you think a question is unclear or whatever, you connect to the Zoom question. All 3 instructors will be there to answer your question. When you get your answer, you can log off and continue your test. Okay. So this Zoom question is just to provide you, like to allow you to ask questions if needed, but you don't have to be connected the entire duration of the test.
Thank you, and thank you for your time.
No problem.